Welcome to the deep dive. We track down incredible sources and, well, we pull out the most mind-blowing bits just for you.
That's the plan.
So today, we're tackling a mystery that's, 5,000 years old? You know Stonehenge. Iconic. Huge stones.
Unmistakable.
And some of those stones, the blue stones, they're dragged all the way from Wales. That much we kind of know. But what if one of the biggest secrets about Stonehenge could be unlocked by something really small, like a single cow's tooth?
It sounds almost too simple, doesn't it?
Yeah.
But yeah, that's exactly what we're digging into today. Our mission is to really explore this fantastic scientific paper from the Journal of Archaeological Science. And there's a related article, too, called Stonehenge's Welsh Roots, a cow tooth's tale.
Right.
And we're going to look at how cutting-edge isotope analysis was used to reconstruct about 6 months in the life of a Neolithic cow. Its tooth was found right there at Stonehenge.
And the connection to the blue stones.
That's
the kicker, right?
Exactly. It uncovers this really tantalizing new link, a potential link, anyway.
Okay, so get ready. We're going to find out how these tiny chemical signals trapped in tooth enamel tell us about diet, movement even pregnancy.
Yeah, it's quite a story, 5 millennia in the making.
Let's start with the tooth itself, our ancient witness.
Right. So we're talking about one specific tooth, an M3 molar, from the right lower jaw of an elderly Bosch's taurus. There's just, domestic cattle.
Okay.
And it was actually dug up way back in 1924 from the ditch that goes around Stonehenge Stage 1 near the south entrance.
1924. And the age is key here, isn't it? This isn't just any cow tooth.
No, absolutely not. It dates right back to the Neolithic period, somewhere between 3350 and 2920 BC.
Which is bang on for when Stonehenge was being built. It's early phase anyway.
Precisely. A direct contemporary. And there's even a suggestion, the jawbone itself might have been quite old when it was buried, maybe 50 to 270 years old.
What, like they kept it? Curated it?
Possibly. The surface preservation was really good, apparently. So maybe it wasn't just chucked away. It might have been significant.
Wow. Okay, but how is a tooth a time capsule? How does that work?
Well, that's the clever part. Cow teeth, hypsodont teeth, they grow layer by layer over time. A bit like tree rings.
Okay, yeah.
So each layer of enamel captures the chemistry of the cow's body, its environment, at that specific time. By slicing this molar into 9 horizontal sections, scientists could basically read it chronologically.
Slice by slice, like reading chapters of its life.
Exactly. About 6 months worth in this case.
So how do you read those chapters? What are the techniques? You mentioned isotopes.
Yeah, a whole suite of them. They used oxygen, carbon, strontium, and lead isotopes. Plus, something called peptide analysis. It's a really powerful combination.
And using a Neolithic tooth was important because...
Because it predates most significant human lead pollution.
Yeah.
From smelting industry, petrol.
Right, all the modern stuff. So you're looking at natural lead signatures from the rocks, the geology.
Precisely. Geogenic lead, which is crucial if you want to trace where an animal might have come from without modern contamination messing up the signal.
Got it. Okay, so let's reconstruct this cow's life. To start with the oxygen, what did that tell them? The internal calendar.
Yeah, the oxygen isotopes, the 18O values in the enamel, they directly reflect the oxygen in the water the cow drank.
Okay.
And water sources, like rainfall in Britain, they change seasonally. So by tracking how the oxygen isotopes varied through the tooth layers.
They could tell winter from summer.
Exactly. They figured out the tooth recorded about 6 months of growth, starting in winter and going through to summer. And this was during the cow's second year of life, like a little internal weather report stamped into the enamel.
That's amazing, just from the water it drank. Okay, so we know when. What about what it was eating? Carbon isotopes next.
You got it. Carbon isotopes 13C tell you about diet. And here, they saw a clear shift.
A shift how?
Well, the values were lower in the winter layers and then rose to a peak in the summer layers, meaning it likely changed what it was eating with the seasons. The lower winter values suggest feeding in a more wooded environment, maybe on leaves, twigs, that sort of thing. It gives what's called a canopy effect signature.
Ah, right. Forest food.
Yeah. Then the higher summer values point towards grazing on open grassland.
So sheltered feeding in winter, open pasture in summer. Makes sense. Okay, so oxygen gives us the season, carbon gives us the menu.
They provide the context, yeah, the backdrop.
But now the big one, where does she go? The movement mystery. Strontium time.
Strontium time it is. Strontium isotopes 87SR, 86SR are a really well-established tool for this, like a geological passport.
How does that work again?
Plants absorb strontium from the soil, which reflects the local geology. Animals eat the plants.
Yeah.
And the strontium ratio passes into their bones and teeth without changing much. So the tooth records the geological signature of where the animal was eating.
Simple enough. So what did her passport say?
Well, this is interesting. The strontium ratio changed progressively in one direction through the 6 months recorded in the tooth. It went from a higher value in winter down to a lower value in summer.
Okay, so a steady change. Does that mean she definitely walked from one place to another?
That's the classic interpretation, yes.
Yeah.
Moving from one geological area to another. But there's a bit of a wrinkle now with newer research.
Oh, what's the wrinkle?
It could mean movement, or it could mean the animal stayed put, but its food source changed its strontium signature. Maybe it was eating stored fodder, like leaf hay collected elsewhere, during the winter.
Ah, so food imported from a different geological zone.
Exactly. Or even moving short distances within one complex geological area, the so-called forest effect again. So that steady strontium shift, it might be movement, or it might be diet change, or a bit of both. It's a crucial distinction.
Right, it makes interpreting it trickier. Okay, so strontium gives a potential clue, but maybe not the full story. And you said lead isotopes were the curveball.
Yes, this is where it gets really, really interesting. Because unlike that smooth one-way street with strontium, the lead isotopes, they went up and down. Peaks and troughs in concentration and isotopic composition.
Not smooth at all. So something different is happening. Tell me about the peaks. Was there one big one?
There was a very clear spike in both lead concentration and its isotopic signature in slice 4. That corresponds to late winter, early spring in the cow's life.
Okay, a spring spike. And what was special about the type of lead in that spike?
Its isotopic signature had what scientists call a Paleozoic model age, which basically means the lead came from really, really old rocks. Ancient geology.
No older than...
Older than the geology that dominates most of England, which is typically Mesozoic. The baseline lead levels in the other two slices matched that younger English geology. But the spike, that was ancient Paleozoic.
And where do you find Paleozoic rocks like that? Anywhere significant?
You certainly do. One prominent area with that kind of ancient geology is the Preseli Hills in Pembrokeshire, Wales.
Wait, the Preseli Hills, as in where the Stonehenge bluestones came from.
The very same place.
Yeah.
So you have this chemical spike in the tooth pointing directly towards the source region of the bluestone.
Okay, my mind is slightly blown. That's huge. But hold on. Why the difference? Strontium changes smoothly, lead spikes. If they both come from rocks, why don't they track together?
Because the body handles them very differently. That's the key insight here.
How so?
Strontium isn't toxic. It basically gets treated like calcium, goes from the diet fairly directly to bones and teeth as they form. Lead, though, lead is toxic.
Right.
So the body tries to get rid of it, but a lot, maybe 94% according to the paper, gets locked away, stored primarily in the skeleton, in the bones and teeth, to keep it out of circulation.
Okay, so strontium reflects recent diet and location more directly, while lead gets stored long-term.
Essentially, yes.
Yeah.
They aren't necessarily tracking the same thing at the same time, but the lead you incorporate might reflect lead you ingested much earlier and stored away.
So, that lead spike in spring, if it wasn't from eating Welsh plants right then, where did it come from? Did they rule out contamination after burial?
They did. They looked at diagenesis changes after burial. But the chalk soil at Stonehenge should have pushed lead ratios down, made them less radiogenic, not created that kind of Paleozoic spike they saw.
So, not contamination, what's the explanation?
The researchers proposed something pretty groundbreaking. They think the lead spike came from lead that was already stored in the cow's own skeleton being released back into its bloodstream, remobilized.
Whoa, lead coming out of the bones. What triggers that? Sounds serious.
It usually happens during times of significant physiological stress, things like old age, maybe breaking a bone, or, crucially, pregnancy and lactation.
Pregnancy, why then?
Because creating a fetus or producing milk requires huge amounts of calcium.
Yeah.
The mother's body starts drawing calcium reserves directly from her own skeleton.
And when it pulls out the calcium?
It accidentally releases other things stored there, like lead, back into the bloodstream. And if a tooth is growing at that exact moment, that mobilized lead gets incorporated into the enamel.
Okay, that's an incredible hypothesis. Pregnancy stress releasing old stored lead from whales into a tooth growing near Stonehenge. But how could they possibly test that? Did they know if the cow was female?
That was the next logical step, and they could test it. They used peptide analysis. It looks for specific proteins, amelogenin proteins, which are coded on the X and Y chromosomes, AMLX versus AML.
So it's like a genetic sex test on the tooth protein.
Pretty much. And the result, a high probability that this Stonehenge cow was indeed female.
It was female. And the spike was in spring, which is calving season.
Exactly. The timing fits perfectly. The lead spike in slice 4, late winter spring, aligns precisely with the most likely time for calving.
So, this ancient cow, 5,000 years ago, was likely pregnant or nursing a calf. That metabolic stress caused her body to release lead she'd stored from her earlier life, potentially spent in Wales, and that lead signature got locked into her tooth enamel as it grew near Stonehenge.
That's the interpretation, yes. It's an astonishing level of biographical detail from isotopic analysis, a life event recorded chemically.
Unbelievable, a 5,000-year-old chemical record of motherhood. So let's bring it all together. What does this mean for Stonehenge itself?
Well, it's the first direct scientific evidence linking cattle remains found at Stonehenge back to Wales. Professor Parker Pearson is quoted saying, "It raises the tantalizing possibility that cattle helped to haul the blue stones."
Wow, cattle involved in moving the stones.
It's a possibility this opens up. The tooth was found in the ditch, remember? The cow might have traveled there alive. Or, given the potential age of the mandible when buried, maybe its remains were curated, transported as significant objects themselves. Either way, it suggests a tangible connection for livestock between the bluestone source area and the monument site.
It adds a whole new dimension. People, stones, and animals making that journey.
And Professor Jane Evans highlighted just how unprecedented this is, getting these details of diet, movement, and life events like calving from half a year in a cow's life 5 millennia ago.
It really underscores the power of these techniques.
Yeah.
But also the complexity, right?
Absolutely. Key takeaways for the science here are multi-isotope studies are amazing, but you have to interpret them carefully, considering the different biological pathways. Strontium and lead aren't always telling the same story simultaneously.
They trace geology, but through different biological filters.
Exactly. You need caution when pairing them for migration studies. And perhaps the biggest breakthrough.
The stress signal.
Yes. That fluctuations in lead, the spikes and troughs, can potentially act as indicators of physiological stress, like pregnancy, in ancient female animals. That's a whole new tool for archaeologists studying animal husbandry and life histories.
Incredible. What a journey we've taken, all from one molar tooth. We've seen seasons change, diets shift, landscapes crossed, and even witnessed the biological echo of motherhood from 5,000 years ago.
It really adds this incredibly personal, individual story to the grand narrative of Stonehenge. It wasn't just about massive stones and mysterious builders. It was also about the life interwoven with that place.
It certainly makes you think. This deep dive into a single cow's tooth shows the past isn't just in the big monuments. It's hidden in the details and the chemistry of seemingly ordinary remains.
Makes you wonder, doesn't it? What other incredibly detailed biographies, what other hidden stories of stress, travel, and life are locked away in fragments? We haven't even looked at this closely yet. What's the next cow's tooth waiting to be decoded?